First of all, I want to thank the speakers for giving me this opportunity to present my work. So this is a joint work with Dr. Arun Kumar. So now I will start. So the outline of my talk is, first I will speak about what are chromatic polynomials, then generalized K-chromatic polynomials. After that, I will define what are BKM-Lie superalgebras and associated graph to that. Then we will see three root spaces, and now in the last we will see relationship between chromatic polynomials and root multiplicities of these three root spaces. So first of all, what are chromatic polynomials? Suppose we have a graph G with some vertex at V and edge set E of G. I will denote 1 to Q, this as a set of Q distinct colors, and this denotes power set of the colors. So this means first one color, second color, that means like red color, green color, these are we have Q colors. So the number of ways a graph G can be properly colored using these Q colors. That is a polynomial in variable Q, that is called chromatic polynomials. Proper colored means two adjacent vertices should have distinct color. For example, suppose this is my graph which has four vertices, and I want to color this graph using two colors, say green and red. Then there are only two ways to proper coloring this graph. So if I have Q colors, then this has Q choices and this vertex has Q minus 1 choices. And this again has Q minus 1 choices because I can't use a color that I have used earlier. It again has Q minus 1 choices. So this is the chromatic polynomial. Total number of ways to coloring this graph. So the next is generalized K-chromatic polynomial. Now we want to color one vertex with more than one colors. So fix a tuple K, which is Ki. This is a set of non-negative integers. We define support of K. Those I such that Ki is non-zero. So now in my definition, everywhere I will assume that support of K is finite. Cardinality of this support is finite. So I want to now defining proper vertex K multicoloring. So if alpha is my vertex, I am choosing Ki colors for this. So Ki distinct colors. The cardinality of alpha is Ki, and if alpha and alpha j have edge between them, then the colors have disjoint. So the number of ways in which we can color this graph using by proper K multicolored using these Q colors. That is again a polynomial in Q. We call that as generalized K chromatic polynomial, which we denote by this. For example, suppose this is my graph. So I have 6 vertices. Now I want to color first vertex by 2 colors, second vertex by 1 color, and third vertex by 3 colors. So this is my bold K tuple. So if I have Q colors, this I want to use 2 colors. So this have Q choose 2 choices. Alpha 2 vertex has Q minus 2, choose 1 choices. For alpha 3, I can't use the color that I have used for alpha 2. So it has Q minus 1, choose 3 choices. So in this way, this is the chromatic polynomial. Total number of ways of coloring this graph. So this is generalized K chromatic polynomial. So I will define what is Borcher-Skaff-Moody, the superalgebras. So first I am defining a Borcher supermatrix. This is just like in Lie algebra. We have a generalized Karka matrix. So this is generalization of that. So the people who don't know Lie algebras, they can consider this is just a matrix whose diagonal entries are either 2 or any non-positive number. So each other entries in that row, if diagonal entries are 2 or anything, these entries can be non-positive for I not equal to j. If aij is 0, then ji entry is also 0. But if my diagonal entry is 2, corresponding all entries in that row, these are integer entries. If diagonal entry is 2 and my I belongs to this side, then all that entries in that row are even integers. So this psi super means we are using Z2 gradation. So this psi is using for grade 1 elements. So my I vertex set, that is Z2 graded, I0 union I1. So this psi will denote 1 grade elements, other elements of grade 0. So I am interested in symmetrizable Borcher-Skaff-Moody supermatrix. So matrix is symmetrizable if there exists a diagonal matrix T such that B into A is a symmetric matrix. So these are the notations. If diagonal entry is 2, I will denote that by I real. Others are I imaginary. Psi real is psi intersection with I real. If my diagonal entry is 0 and I belongs to psi, then I am denoting that by psi. So now BKM-Lie superalgebra. We can consider just as a take a free super algebra, impose some relations. So we will generate a free algebra by that. So take Chevalier generators EI, FI, and HI corresponding to I belongs to I. So these are the necessary relations that we need to decompose this into root spaces. This gives triangular decomposition. And next, these relations give us complete structure of BKM super algebra. So we can just assume that take a free super algebra and impose some relations. That will give us some BKM super algebra. So this is another way of defining this. Take a free super algebra generated by these generators. First, we impose the necessary Chevalier relations. It give us triangular decomposition. Then these are we impose if this Aij is 0, then these relations, partial commuting relations, these are relation on these root spaces. So the final relations give us, by quotienting all the relations, became these super algebras. So our interest is in free root spaces, which are those root spaces which are independent of these Serre relations. If we quotient by Serre relations, the root spaces which are unaffected, that we call as free root spaces. So now we want to associate a graph to this Lie super algebras. So that graph we will denote as quasi-Dynking diagram. So let L psi be a BKM Lie super algebra with associated matrix A. Then let G be any graph whose vertex set I will denote by alpha I for I belongs to I. So this is a Z2 graded vertex set. And edge set, if my Aij entry is non-zero, then I can put an edge between alpha I and alpha j. So this is the only condition. So this graph gives us some information about BKM Lie super algebra, not much. So this just tells us whether two roots are connected or not. If Aij entry is 0, then these roots are not connected. So for example, consider this matrix A. So now this is 6 by 6 matrix, so I have 6 vertices. So alpha 1 and alpha 2 are connected because A12 entry is non-zero. Alpha 2, these 3 entries are non-zero. So that is why alpha 2 is connected with alpha 1, alpha 3, and alpha 4. So in this way, this graph is called quasi-Dynking diagram of G. So suppose this is my bold K tuple. Then this is a graph we can associate a generalized K chromatic polynomial with this. So this is a generalized K chromatic polynomial of this graph. So now we want to associate this with root spaces. So what are three root spaces? So these are the notation. Set of roots I will denote by delta. Alpha I for I belongs to I. This is set of simple roots. Q is root lattice. Q plus is positive root lattice. This we already know that I is Z2 graded set where I1 is our fixed psi in the starting and I0 is I minus psi. So any element of root lattice is of the form Ki alpha I. So weight of alpha we will define as bold K tuple Ki corresponding to I belongs to I. Support of alpha is defined as those I such that Ki is non-zero. So we can say alpha is free if Ki is less than equal to 1 for I belongs to I real union psi 0. So now this relation, this lemma given in this book of Wakimoto. So in this we will see the construction of how roots are defined. So if alpha is any positive root not equal to alpha where I belongs to I imaginary and support of this is connected, then alpha plus j alpha is a positive root for all j belongs to positive integers. So there are large class of roots. So now we will need some terminology, bond lattice. So what is bond lattice? If suppose we have this bold tuple K like we see in example 0, 0, 3, 0, 0, 3. In that case, this is corresponding to my alpha 3 and this is alpha 6. So I consider this root 3 alpha 3 plus 3 alpha 6. So now I can partition this in such a way like I can consider one partition alpha 3, alpha 3, alpha 6, alpha 3, alpha 6, alpha 6. So I can write in such way such that each set itself, when we are seeing the graph of this should be a connected graph. So in this way, this LGK corresponding to bold K, this is bond lattice where J is J1 up to JL such that Ji can be equal to J of J. Like in my example, I have taken alpha 3, alpha 3. So these two can be different at J1, J2 in this bold J such that their union is exactly alpha is occurring Ki times. So that is partition of our root space in this set. So this is called weighted bond lattice. So multiplicity of each Ji in J is denoted by this symbol. Now taking all elements from Ji, corresponding alpha sum is giving us beta of J. Dimension of this root space is known as multiplicity of this root. So this is a lemma which relates weighted bond lattice with roots. So if we have picked any element from here J, then corresponding we can attach a root. J1 corresponds to beta of J1. If my J1 is alpha 1 alpha 3, then my beta of J1 is alpha 1 plus alpha 3. There is some condition on these Ji's. So this is my J1, J2. So this is corresponding to our bold key. So this lemma gives us the bijection. So now we will give the relationship between chromatic polynomials and root multiplicities. In 2015, Venkatesh and Vishwanath, they relate chromatic polynomials with root with root multiplicities of Kac-Moody Lie algebras. So this relation gives us a relation between root multiplicities of Kac-Moody Lie algebra and chromatic polynomials. So after this, in 2018, Arun Kumar, Kuz and Venkatesh, they generalized this result to Bouchard's Lie algebras. So for any bold K tuple, they relate from a generalized K chromatic polynomial with root multiplicities of these Bouchard Lie algebras. So our result is generalization of that to Bouchard's Kac-Moody Lie superalgebras. So in this case, the next thing here comes up psi. So we relate generalized K chromatic polynomial with multiplicity of these root spaces. Free root spaces. This condition is for the free root spaces. So as a corollary of this result, we are explicitly getting multiplicity of this root space G of eta P. Where this symbol means mu of L is our Mobius function. So this formula gives us if alpha we have even root, then this formula we can use for multiplicity. This is for odd. So for example, the example that already we saw in previous graph. So this is generalized K chromatic polynomial of this graph. If we choose the compute in this way, so we are getting the multiplicity of root spaces. So these are the references. Thank you.